Today we're gonna speak about ROS, Erlang, a bit about robots, but also about communications, distributed systems and networks, a lot of stuff. So, how do I change slide? Okay, like that. Okay, let's for starting, couple of words about me. I'm Luca. I come from the Adapt Lab in the University of Milano. And now I'm working for Pristritzingen. And what I'm presenting today is indeed my graduation project that I basically graduated with. Originally, this is an EF funded project. And so with the help of these people, I graduated, and I also am here today speaking about this story, basically. Let's start from the first part of the name, so you need to understand what a robot operating system is. And by the way, it's not really an OS. What ROS really is, we can say it's an ecosystem, really. It's like a distribution of open source software you can find online. And if you want to build a robot, it happens to be really useful. Like, for example, in 2020, they reported like 500 million downloads. So it's very handy because when you have to build a robot, you don't want to reinvent the wheel every time. So you want to access like a library for communicating, because most of the time you have either a complex robot with multiple components or a swarm of robots. So you most of the time have a network. And also you access a whole ecosystem of packages that implement drivers, components already ready, interfaces that you can share with other users in the community, so you can have the same messages and be interoperable. And also they provide a build system, tooling for debugging, introspection, all kind of handy stuff. We will focus on the core feature of ROS. That is a ROS client library. First feature of the library are messages. Messages can be described with the files you see on the left. And as you can see, they get pretty much complex because you can compose messages with other messages, so you can have nested types, of course. For example, a point, what is that? Pose is composed of a point and a quaternion, etc. And with these messages, you basically define types. You give a name to a message and a type, you build a topic. With that topic, you can like publish or subscribe to the topic. And what ROS does for you is that if you publish on the topic, everyone that subscribes to the topic will get the message transparently. So you just don't bother. ROS gives you the middleware for that. So you can like publish, a sensor publishes, and you have a central logic, and you publish to an actuator topic, and then the actuator is subscribed to the topic, stuff like that. And what ROS does is that uses these messages to implement more complex services, like, for example, services. And services basically just, they did like, they created, okay, the server, then it's a publisher on the reply topic and a subscriber of the request topic. So with two topics, you build a service. This is a synchronous call. You wait, you get a reply. And also you have a type for that. So in the higher part of the file, you have the stuff you put in the request, and lower after the dashes, you have the reply. Or you can go even more complicated because you are basically building a robot. The robots usually do tasks, so you can have services and topics together and form a more complex service called actions. And you can request action you want the robot to perform. The robot can provide, they can store the goals, store the results, cancel the goals, give feedback, so you can do a lot of stuff. So ROS is very, like, publish, subscribe model, too soon. Okay, publish, subscribe model, optimized, and for robotics needs, of course. But this is really a communication problem, right? So currently, pretty much you can program it in Python and C++, but underneath is pretty much all C. And what they're really solving here is a communication problem in a distributed, it's a distribution problem where you have multiple nodes in a peer-to-peer network. It's a communication problem. They are exchanging messages. That's the main problem this library solves. And you want ROS for this library, then also for all the other packages that are useful. But this is core component. So with ROSiE, the central idea is, why don't we use Erlang that was born for telecommunication to enhance or maybe build in a better way this service and basically use Erlang to solve the communication problem that ROS client library offers. So we can view this project, or at least understand the interest that's behind it from two point of view. From the robotics world, what you could get if you would have like ROS2 in Erlang would be, of course, you get Erlang scalability for tolerance. You get a lot of stuff if you just write Erlang in the right way, for granted, like for free, runtime upgrades, and overall you can build a robot that has just high availability, and if you want a robot that never stops, that it's fault tolerant, etc., well, would be very handy to be possible to write that in Erlang. And for Erlang, of course, you can imagine that even if you are not interested in robots, you now can like access a robot network because you know that others are already using ROS. Maybe you say, okay, I can put also my ROSiE robot that basically is ROS, but I will do it with my technology, with Erlang, etc., and still be usable, interoperable with the ecosystem offered by ROS. So we want a good ROS solution usable by the ROS community, but also we want a good Erlang solution because to the problem. So we don't want to mix stuff in weird ways. We want to have the best of the best from both worlds. So what we have kind of the requirements to achieve this. We want full interoperability with ROS2 because otherwise no one that is using ROS2 will try Erlang because why would they do that? We don't want to replace ROS2, but also we want pure Erlang from the top to the bottom because we want all the scalability, fault tolerance, and blah, 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 also on the full stack, basically. And that's for the protocol and the library, but then there are other stuff like you saw before, types. So we need also a bit of the package ecosystem. We need a way to be able to write our Erlang application, but there are also ROS applications. So we need to merge and bridge REBAR3, that is the usual build tool for Erlang, with the ROS2 ecosystem. So we need to do a bit of stuff. This shows you the current ROS2 software stack. It's pretty elaborated. We have, at the higher level, bindings for 2 languages. And then middle layer in C that basically implements the main logic of the library. And then they have the smart choices to delegate the service of actually distributing information over the network to other providers, like DDS vendors. So they use the DDS technology, that is a specification from the OMG group. By the way, the reason why they have this tall stack is because, okay, if you want to play with robots, you usually use Python because it's more simple. But if you need highly efficient robots, you have restricted resources, you high exchange of messages, etc., you need to rely on C++ library because C++ library allows you to access executors. There are third-party libraries that basically implement threads, synchronization, scheduling, so pretty complex stuff. There's a lot of research in the ROS world with executor libraries where companies develop their executor libraries for domain-specific needs because any domain needs its optimization, of course. Then C layer to don't repeat code, and then different bindings. So you can switch DDS vendor between an open source solution or like a paid solution. There are many closed or open software there's out there. And a couple of words about DDS. So DDS basically implements that first feature of ROS. If you remember messages, we had just topic. And that basically is a one-to-one mapping nearly to what DDS already offers. So DDS use spawn endpoints. It can be a writer or a reader of a topic. The topic is a name and a type. And DDS doesn't care about serialization. So ROS provides the serialization. And then DDS is just there to give you this virtual global data space and this transparent. So I mean, it's really, really handy. And this is a good standard, and the implementation are used in many, many fields. So now we want all this stuff in Erlang. So basically, if we achieve that, we basically not just using Erlang on the cloud, we can use it on the edge, because robots are quite near the edge. And this is what is like to look at the stack, software stack of ROSiE. That looks simple. That, by the way, is also a good thing, because now the semantic changes. Before we were looking at libraries, where at the top we were putting executors. Now we have applications, not libraries. We have processes, no more threads. By the way, are all gen servers, all are supervised. And we also provide an implementation of DDS fully in native Erlang, without NIFs, other stuff. And of course, to be interoperable, we are not using Erlang distribution, because they don't have it. So we also implemented another specification that is the RTPS DDSI. This is the interoperability protocol you need to basically make sure that every DDS vendor on the wire serializes data in the same way, so you basically have the same layer 5, the ROSiE stack protocol, So we can interoperate over UDP with any implementation currently available of any robot written in ROS, also visualization tool, as we will see later. And that's just to say we achieve interoperability on the protocol level, but you also need to achieve interoperability on the type system. And those types usually are online in a repository you find on GitHub, and you need to access those data and serialize that data in the same way that data is described in like custom language provided by ROS. So we need a way to actually get the stuff automatically, and automatically compile it, and have it accessible at runtime. So RIBAR3, of course, allows that, eases the process if we write plugin for this thing. So usually you write your app inside your RIBAR3 project. So you want to your robot app. So what you do is you depend on ROS. ROS depends on DDS. And by the way, if you don't care about robot, you say, I just want DDS, you can go to the project directly and just took just the DDS project because it's standalone, basically. And then you have these two plugins that work together that I wrote to basically automate this stuff. So in the top, you can imagine you have the main root RIBAR3 config of your project where you specify a dependency. So let's say that you want to publish the vector3 message, okay? You need that type. You know that that vector3 message stands inside a ROS2 package called geometry messages. So you just need to, like, of course you depend on the plugins, but then you write geometry messages, and then ROS2 galactic. Galactic stands for the distribution. We are looking to basically find the repository, where the repository is. And my plugin, what it does, it goes there, it finds, how much time do I have? Okay. I ran it too fast, maybe. Maybe, yes. So basically, yeah, I go to this YAML file that is in a repository where all distributions are listed. I find the package directory, because sometimes you have one package in one repo or multiple packages in the same repo. And what I do is I call the Git dependency, the Git resource provider. And what it does, it fetches the repository. I get the package directory I want. I extract mainly all the interfaces, so .msg, .srv, and .action. and I generate a ROSiE project directory. And with the package XML, that's very important because, as you saw before, you can have a message dependent on other messages. At that point, you need also those ROS packages because sometimes the dependency is the same package, another package in the same repo, or another package on another repo. And so you put those dependencies with the same syntax inside the ROSiE config. So when ROSiE tries to compile, well, of course, it will hook to my plugin again, and so we can resolve any nested dependency. It's quite cool. You can automatically resolve any dependency tree in the ROS2 ecosystem just with this plugin, and then it compiles them. So before the Erlang module compilation step, we have a hook that we compile all messages, services, and action files. The most simple process is the compilation of the messages because you just need to generate one Erlang module and one header. The module takes care of serializing and parsing data from the wire, from to the wire, so how you actually serialize that message. And the user will give to the library just the name of the module, so that it will be the library to call the module. And then it can include the header, because with the header you have a record definition that basically mimics the MSG file. So you have like default types or kind of useful stuff, and then you fill your record, you pass the record to the library, and everything at runtime works properly, and messages are serialized and sent to other peers. Okay, and anyway, I don't know if I was too fast, and we can go over other stuff later if I was too fast. Now I basically ran over all the stuff. It was important to mention. Now we'll go on the demo. So today I took here a robot. The robot it's pretty simple. Doesn't fly, at least. We have 4 wheels. That the most important stuff of the robot. We have 4 independent wheels controlled by 4 HB5 modules. Those are DC motors on the sides, so we can control each wheel. And then we have a sonar on the front. And those, by the way, the modules are all PMods. And we have sonar on the front and a navigation module at the center. So we can also get like accelerometer data, temperature, gyroscopic measurements, stuff like that. And of course, the heart of the system is powered by the GRiSP2. So these are a couple of information. But by the way, if you watch the peer presentation, you already know about GRiSP. And this board allows us to do quite a cool thing, because we are not only running right now, it's already running, we're not just running, it doesn't grip much, but it's working. So we're not just running ROS2 complete in Erlang in the full stack, so we are talking about just Erlang code. But we're also doing that right on the hardware without an operating system, while on ROS, 90% of the time you need an operating system, and also it's not supported very well on all platforms, so you need to choose. Okay, to development it's harder, but yeah, I mean you need an operating system usually. So what we are going to do with this robot today is some kind of delicate thing, and not so easy to achieve. I mean, I'm not saying you need to do this every day, but the thing is, now by having a robot, a ROS robot in Erlang, you can do this. Usually you can't in the standard implementation. So we have this robot, and it doesn't grip much, but its bug is that when it sees something on the front, it should just go back. Okay, if he sees a lot of space ahead of him, thanks to the sonar, he should go forward. The problem that 0.1.0 version, the code for the wheel says forward to all 4 wheels, but you need to say backward to the wheels on the right. Otherwise, because the motors are mounted in another direction, and so you get this stupid bug. Well, it basically goes left instead of going backward, and goes right instead of going forward. So the fix is pretty trivial. But the thing is, imagine this is a more complex robot, like on a distant planet, something you don't want to stop, something you can just go there, swap the SD card, flash another SD card, and put it there. You want to, you need to do this at runtime without stopping the robot. So already in my working directory, I'm gonna switch in a moment. I have already set that up, so I already fixed the bug. I already checked out to the version that fixes the bug, and I'm helping myself with a plugin to generate the app. But by the way, the app for this upgrade is pretty simple because we are just changing one module, the module that controls the motors. So we just check out, and then we generate the release, the app, then the rel app from the app, and then we build a tarball. And this is all done in the default build directory variable 3. What I had to modify and change to have this stuff working is like taking the usual install upgrade script, that is an script you find in the release directory that is used to start your Erlang application or upgrade it, because you usually call the start script that calls this other script underneath when you need to upgrade a release. Because I had to modify the script and some custom stuff, because usually an upgrade procedure in Erlang is done on the same file system. I observed this looking at the code of the script. It's for, you want to upgrade the ROS node, but on the same file system, this remote node is running. So you unpack the tarball on its file system. Okay, so you are forced to launch the command from a remote shell. Instead, we want to use Erlang distribution all the way. So we want to really remotely upgrade the command. So we just the network. We don't want to open a remote shell with SSH, because we don't really have OS level SSH. We just have the Erlang machine here because we don't have an OS. We want to just use remote procedure calls. So I tweak the code. What I do, simply I copy the tar with the remote procedure call in a directory where it's suited on the GRiSP. I override the GRiSP, that is the text file that says the command that chooses the release. So my upgrade is basically stays there if the GRiSP is rebooted. And then I ask the release handler with a remote procedure call to, of course, unpack the release. And the effect is that we want to get 0.2 running on the robot. So, okay, this other stuff. While I'm doing that, so do you see my, okay, VS Code. Okay, I already done the other stuff, so we just have to launch the upgrade script that runs that command. I want to get it bigger so you can better see the logs on the console. Okay. It says node is not there. I fucked up anyway. It should say, okay, it said something. It said, okay, release not found. So we already copied the tarball. And right now, it's still bugged. Why? Because it's unpacking the tarball. So the tarball is like 6 megabytes. We don't have an Intel Core i9 on this board, so it takes a bit. Around 1 minute and a half, because it says needs to unpack the tarball. And but when it does, just needs to load the modules, and it will change the behavior, but it will also report us with the result. And why he does it, I also can show you that we are visible on RQT, that is basically shows up, lets you see ROS networks. And if I open ROS2, it picks up, it discovers our robot on the network, and basically receives sensor data. This data is, of course, data serialized, how the ROS2 interface says it should be serialized. If I, oh, fuck. Damn. Okay. No, 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 no. So the problem if he goes onward if he doesn't see anything, and so it's hard to control. No. Okay, I have a solution. Okay, maybe he likes this distance. It has like a safe distance. So he's too near for him, and if I put it there, it's too far, so he goes. Yeah, well, it's fine for now. How much time do I have? Okay, I can try other stuff. Yeah, I'm too fast. Damn, that's a problem. Too many questions later. Anyway, on the left you have argvids. I don't like argvids. It's like in alpha. It's messy. But anyway, you can like set up, choose the topic. So for example, the temperature. If I stick my finger there, it gets warmer, the color. So you can put any ROS topic. For example, it's picking up the acceleration topic. So it's finding the ROS node on the network. And if I update RQT, and I say I want it to fit the bigger, I want it bigger. Well, anyway, do you see something? Okay. Basically, that thing means we have a node called GRiSP, and that the arrows say, okay, we have published, that node is publishing on visualization marker array, sonar, temp, acceleration. TF stands for transform, and then the ugly thing on the right is the ROSiE node, so the GUI that is actually showing us the 3D models, etc. And as you can see, it's responsive, it's giving us data, etc. Okay, let's say that we can do also other stuff. So this was a release upgrade done at runtime. Pretty sketchy stuff, but it works. As you can see, it printed the unpacked release successfully, install version 0.2, and new release made permanent. So we have done it, demo succeeded. So we can do some extra stuff. Let me go back to the slides. Okay. Okay, the other stuff you can do while developing, okay, let's say we are in a more comfortable situation, we are just developing the robot. So we can, of course, connect over serial with this command, so it's easy with the GRiSP port, of course, that's a wrap there because using Pico.com alone is not really comfortable, but then you define the bad way that you connect over serial, that's just standard thing for the GRiSP board. And then you can, of course, remote shell. You don't have an OS shell-like, but you can remote shell with Erlang and just run commands directly on the machine. Or you can do a pretty cool stuff that I think that for a robot developer it's pretty cool. So you can like hot loading, like net loading modules with the REBAR3, the REBAR3 shell. And that's very cool because we can change the behavior in development without having to do a release upgrade. Of course, it's not persistence of we reboot the robot, it will go away. But if we want just to tinker with the robot, like we are in prototyping, or we just, I need to change the value, let's see how the robot goes. Maybe the robot is in a state, in a later state, after half an hour work, you don't want to restart the robot to test this particular code change. You just want to inject the code change of multiple different times when the robot is already in an advanced state. That would be really useful, I think. How do I exit? So back to my terminal. What do we want to do? Okay. Okay. If we go down, you see here, I have the range. I have a function that gets the range from the sonar. And it says, OK, if you are less than 20 units, you go backward. And if you are more than 60, you go forward. OK, let's lower them. Like, I want 10. I want like 30. or can go lower, like 50, but then depends how the robot handles it. Maybe 25. And then the other thing is like stop, so we will stop between 10 and 25. So I already set up, as you saw in the slide, I have a configuration when if I type ROS2 free dev, I already launched the shell with this name, with the same cookie of the node running on the GRiSP. And I also launched an A script that for me pings the GRiSP. So it should, we are compiling and print a lot of ugly stuff because need to clean up those plugins. But anyway, we are in the shell. We compile everything, so the code is updated. So I just have, I should work as if I do NL like NL robots GRiSP, it should work. But it worked. It didn't fire up rockets, but we changed the behavior. I imagine my robot does all wonderful things like machinery, moving stuff in a factory, and well, you do. I'm changing the hard code while testing. So this is pretty cool. I mean, I think I can also like code more and change more. If you change the state, of course, that gets more complicated. Upgrades are always complicated if you have a complex application, of course. This is simple, but it's possible, and this is a great advantage given from Erlang, in my opinion. So I'm done. I was really fast, so if you want me to go over again the thing I said, and I just leave this last slide. Can you please go? I need to publish still the repository with the code. You can access codes from the whole ROSiE project. Is open source offline, of course. All code related to the GRiSP also. And also, I've just put also the RoboGRiSP repository, but it still is not. We will make it public in minutes because I'm not allowed to change permissions there. Anyway. We'll do that. Anyway, I'm done.
Thank you very much, Luca.
Thank you very much.
We will get to questions immediately.
Thank you.
You did not follow the principles of Erlang, and you didn't let it crash, but we will allow that. Let's see, we have some questions online. Is Karen in the room or online? And if so, can they unmute and ask? I'll ask for her behalf. So the question is, are you using Erlang to write the nodes for ROS2, to write the drivers for the robots, or both? Are you making drivers for this?
We have the drivers for the GRiSP, of course, because the hardware is the GRiSP, and we have drivers for it. And I also modified and updated some drivers just for the demo, because we had multiple HB5 modules. So I had also to modify the code that, by the way, is open source. So everyone can do that. Maybe we'll merge also these changes. So I tweaked the drivers, but usually I don't do that. I'm not in robotics usually, so I'm more on the Erlang side.
But you normally write the logic for the logic of the robot and not the drivers, like the low-level stuff in Erlang. Right?
For this demo or for the library in general?
For anything.
For everything? I wrote the driver were already there, I just modified it, but I wrote the entire ROS2 stack, so also on down, and the code for the demo. So if you saw on VS Code, there's not much code really, because the robot is pretty simple. So we have like a supervisor module to like isolate the wheels, a general RoboGRiSP module, there's 168 lines. It's really and there's a lot of code, for example, to serialize stuff for the visualization, because you need like to give transformation, because the visualization tool must position stuff in a 3D world. So it's boring stuff related to visualization, just that.
Peer has contributed that the answer was yes.
Yeah, I don't. Maybe I didn't catch that one.
Another question from Hideki Takase, in the room or online. Would you like to unmute and ask? Otherwise, I will ask. Could we use ROSiE from Elixir or a Nerves application?
Elixir? Okay, I have no experience with Elixir because I just write Erlang for like less than 2 years. So I work really seriously just 1 year. So I don't know how Elixir works, honestly. But they told me that you can call Erlang from Elixir, like a library. So you should be able easily to use the ROS2 stack I wrote also in Elixir.
To interface from there as well.
I think it shouldn't be any problem. If you can call a Erlang library, you can also call ROSiE.
Cool.
That's fine.
And it would work on Nerves as well, is what Peer is contributing. And Hideki has one more question. How about quantitative performance compared with RCL C++ or RCL Pi? For example, RTT time, network scalability. Are these dimensions with Erlang?
Performance right now wasn't the priority. So you must consider this library, ROSiE, like an experiment. So it works, like I demonstrated, but I think actually performance are not good, but for the simple reason I didn't want them to be performant. So I want them to be simple and working. But on the practical side, you just need the will to put the effort and just implement even just the standard performance tips they give you in the DDS specification that would already get you a lot better performance. So you can totally achieve that. Currently, you don't. So if you don't download ROSiE and you are open Wireshark, and you say, oh, a lot of those packages, what a waste. Yeah, but we are like prototyping stuff, so actually don't care. But if you want, we can, of course, easily improve stuff.
So it's in the make it beautiful part now. It's like first you made it work, now it's also beautiful.
That's important, make it work.
And then it will be fast.
Then faster, whenever you need.
More questions from the audience? Or challenges for the robot to perform? Peer has a question. No. Got the mic.
Does this work? Yeah. So this visualization that we are showing, can you say a little bit more about that? Like,
the visualization.
What is this? Why is this? I mean, this is a ROS node, the visualization.
Si.
So I was missing that.
You said, we? Sorry?
Just explain what it actually is.
Okay. Basically, on the logic level, on the network level, this is acting like any other ROS node. So for the ROS library, the library doesn't care if it's a sensor in the local host where you have an Ubuntu machine. It doesn't care if it's a robot, if it's a program on a server. The library is just a communication library. So right now, you can view the simulation like if it was another robot communicating with our. The simulation itself is a tool. This one here, especially ROS2, is thought to be like a debugging tool. So you have your robot. Think about a robot with a LiDAR. So you scans space in a two-dimensional way, okay, and publishes a point cloud data. And with ROS2, you can, for example, visualize also point clouds. And so you can see what the robot sees, and you have a better understanding of the output of the robot sensor. It's not for simulation. For simulation, they have other tools like Gazebo. This is for just debugging. And the way you set up your work here, the interface is ugly. And you have, for example, I want to visualize the data about the sonar. So my robot does the job of taking the sensor data and publishing it on the topic. From the ROSiE side, I used one of the default plugins called Range. And the topic here, already the application sees other compatible topics. In this case, it shows up just Sona, because /Sona is the only topic on my local area network. And then you can set the def, history, policy, reliability. These are all stuff that ties in the lower DDS level, because a topic is not only a name and a type, but is also a bunch of quality of service settings that define the compatibility between two topics. So two topics may not be compatible. And also the temperature, I did the same thing. And then you also can tweak for example, the dimension of the big gray rectangle you find there, the parallel the stuff. I defined it in the robot. So the robot is saying how much, the dimensions, the measurements of the 3D stuff you see. Or you can load any 3D model. And if I shake the robot, you get accelerometer stuff. Or maybe it just crashes. No, it's okay. I'm publishing data every 50 milliseconds. Usually it's 100 milliseconds, but I overclocked it for this demo.
Cool. We have one more question from Phil Dempster. Is he in the room, or does he want to unmute and ask? It's a philosophical question.
It was a facetious question, really. When do you think Erlang robots will become self-aware?
I don't know how much scary that sounds. Self-aware in which sense? I mean, if you put something like an AI, trained AI, if you load a trained AI model on that, and then you attach it to sensor and actuators, I think you can do pretty anything. So yeah, it depends how well it's trained.
I came up with a question on the spot. Does the robot have a name?
RoboGriSP, I think.
RoboGriSP. Okay.
Let's call it that.
Okay, that's all for today. Thank you very much, Luca.
Okay,
and the RoboGriSP.
Thank you for listening to me.